Non-Euclidean Geometry by Roberto Bonola. Chapter 1. The Attempts to Prove Euclid's Parallel Postulate. Section 2. The Greek Geometers and the Parallel Postulate. Proclus. Section 2. Even the earliest commentators on Euclid's text held that Postulate 5 was not sufficiently evident to be accepted without proof, and they attempted to deduce it as a consequence of the other propositions. To carry out their purpose, they frequently substituted other definitions of parallels for the Euclidean definition, given verbally in a negative form. These alternative definitions do not appear in this form, which was believed to be a defect. Proclus, 410 to 485, in his Commentary on the First Book of Euclid, hands down to us valuable information upon the first attempts made in this direction. He states, for example, that Posidonius, 1st century BC, had proposed to call two equidistant and coplanar straight lines parallels. However, this definition and the Euclidean one correspond to two facts which can appear separately, and Proclus, on page 177, referring to a work by Geminus, 1st century BC, brings forward in this connection the examples of the hyperbola and the conchoid, and their behavior with respect to their asymptotes to show that there might be parallel lines in the Euclidean sense, that is, lines which produced indefinitely do not meet, which would not be parallel in the sense of Posidonius, that is, equidistant. Such a fact is regarded by Geminus, quoting still from Proclus, as the most paradoxical in the whole of geometry. Before we can bring Euclid's definition into line with that of Posidonius, it is necessary to prove that if two coplanar straight lines do not meet, they are equidistant, or that the locus of points which are equidistant from a straight line is a straight line. And for the proof of this proposition, Euclid requires his parallel postulate. However, Proclus, on page 364, refuses to count it among the postulates. In justification of his opinion, he remarks that its converse, the sum of two angles of a triangle, is less than two right angles, is one of the theorems proved by Euclid, Book 1, Proposition 17. And he thinks it impossible that a theorem whose converse can be proved is not itself incapable of proof. Also, he utters a warning against mistaken appeals to self-evidence, and insists upon the hypothetical possibility of straight lines which are asymptotic, pages 191 and 192. Ptolemy, 2nd century AD, we quote again from Proclus, pages 362 through 365, attempted to settle the question by means of the following curious piece of reasoning. Let AB and CD be two parallel straight lines and FG a transversal, figure 1. Let alpha and beta be the two interior angles to the left of FG, and alpha prime and beta prime the two interior angles to the right. Then alpha plus beta will be either greater than, equal to, or less than alpha prime plus beta prime. It is assumed that if any one of these cases holds for one pair of parallels, for instance, alpha plus beta is greater than two right angles, this case will also hold for the other pair. Now, FB, GD are parallels, as are also FA and GC. Since alpha plus beta is greater than two right angles, it follows that alpha prime plus beta prime is greater than two right angles, and thus alpha plus beta plus alpha prime plus beta prime is greater than four right angles, which is obviously absurd. Hence, alpha plus beta cannot be greater than two right angles. In the same way, it can be shown that alpha plus beta cannot be less than two right angles. Therefore, we must have alpha plus beta is equal to two right angles. Proclus, page 365. From this result, Euclid's postulate can be easily obtained. Non-Euclidean Geometry, a critical and historical study of its development. This book was written by Roberto Bonola, professor in the University of Pavia. It was published by the Open Court Publishing Company, Chicago, 1912, and is now in the public domain. Read by Jim Renholt, with programming and illustrations by Jim Renholt, 2019. Thank you for listening.